So at this point, I'd like to transition to a deep dive talk by Egor Krav. Egor, thank you for joining us. Egor is the head of AI at Wise, where he has been working on, he's going to tell us about some of his work on auto-causality. Thank you, Egor.
Yes, I'm Ray, and thanks a lot for inviting me. And indeed, I will talk about combining my two favorite topics, which is AutoML and causal inference, to make better use of, to do better A/B testing. So causal inference, as probably most of you here know, is a wonderful, complex topic. I absolutely loved the Causality second edition book. I read it twice and maybe even understood half of it. Apologies, I need to share my screen, yes. It is sharing. Perfect. So you probably see now. Most of you have probably read one of those wonderful books by Julia Pearl, and all the wonderfully complex examples therein. But I thought to actually add value using this, let's do the simplest thing, the simplest possible thing. Let's look at A/B testing. Now, all of you probably know what traditional A/B testing looks like. And you read things like A/B testing is the golden standard for learning cause and effect. So you have two different groups among your audience, and you expose them to different versions of something. A website, a treatment, maybe you send an email to one group and don't send an email to another. And you measure the average difference in some target variable. For example, how much your customers spend in the 3 months following the treatment and non-treatment. And this is all well and good. Everybody does it. And of course, if you need to understand your customers, you need to do something like that. But it has downsides. First of all, when you think about it, it's kind of wasteful because you have to typically collect hundreds of thousands, if not millions of data points to get just one Boolean. Is it significant? Or maybe a single number, which is the effect size. And the reason for this is because you treat differences between customers as noise. You want to average over them. And so if some of your customers hate your email and others love it, you'll just see the zero average. And finally, for those reasons, it's also kind of hard to sell to product teams. If we've already taken the effort to build a new version of a feature, then we probably assume it'll be useful. And in any case, it's already built. So how do we justify additional resources to run the test? And how can causal inference help with this? There's a couple of ways. The most important one is that you can estimate impacts not just at the average level, but at the level of individual feature vectors. And throughout this talk, I will look at these two possible graphs. The first one is your classical A/B testing scenario, where you have treatment that's randomly assigned, and you have some customer features, something you know about the customer, how much they spend in the last 3 months, for example, what region they're from, etc. However, there's also a second option. You don't have to have a purely random treatment. You can also, for example, have a treatment that's random, but with the treatment probability varying depending on customer features. And that's already a scenario that classic A/B testing cannot really deal with. So how can causal inference help? It will, first of all, estimate impact per customer, or rather per feature vector, as a function of that customer's properties, and usually even supply confidence intervals for that. So now you can take the same data set you collected during A/B testing, enrich it with customer features, and you get customer segmentation by impact of your intervention. This means that the fact that all of our customers are different is now a valuable information source. and not just noise that you want to average over. And the promise of this approach, which I have not yet verified, but which looks plausible and which we will verify, is that this should also allow you to need lower sample sizes to actually get significance, which means faster testing cycles, and that's a good thing. Now, so much for the idea. Anybody who tries to actually apply causal modeling will have found that it's not easy. You have several wonderful causal inference packages available. First and foremost, of course, DoWhy and EconML, but there is about half a dozen others. And even within one package, such as EconML, you have multiple models. See this wonderful flow chart helping you to choose a model from EconML alone. And those models have APIs which are varied. For example, again, just inside EconML, there are four or five different names for the propensity to treat function in the different constructors. Each model has its own set of quirks. Sometimes you need to tell the model that the treatment is categorical, sometimes you don't, etc. But all of this you can read in the docs. But then also most models require a choice of hyperparameters, and most of them also need a choice of regular machine learning regressors or classifiers supplied as model components. And all those choices are left to the user. So you have plenty of choices, lots of quirks to figure out. And even after you've done all this, it's not obvious how to combine different models after you fit them. Measuring counterfactuals is hard enough. How do you do out-of-sample testing for counterfactual estimates? So I'll cover this bit first. So when you compare causal models, there is basically two to three approaches, depending on how you count. The first one, which is the one you see most in the wiki and in the literature, is Kinney curve based. So you build a curve that's broadly similar in spirit to the ROC curve for classifiers. And you compare the curve achieved by the area under your model's curve to the perfect curve and to the random curve, and normalize it in some way to make it comparable. And it's nice, but it's quite hard to interpret when I tell somebody, okay, this model has a Kinney area of this much. What does it mean? And for that reason, I find myself drawn to another metric, which is policy value, also catch acronym ERUPT, estimated response under proposed treatment, which is that once you have a model, you can specify a policy. For example, you treat every customer where the impact predicted by the model is positive. Or you treat every customer for which every impact predicted by the model is bigger than X. And then you actually can have, if your original sample was randomized, you can have an unbiased estimate of any policy just from that original random sample. And that is a number that's measured in dollars or percentage point conversions or things that matter to the business. And finally, I've looked at the R-score, but for these purposes, I found it has too many moving parts. It's itself basically a model in its own, so you have to train it from scratch every time. I'd like the scores that we use to be simpler and just purely math-based, which these are. And just so the two kind of policy value or ERUPT versions that we already have in the library, which I will shortly present, is that first of all, just regular, if the treatment effect is positive, then treat. And that's the first policy. But in many cases, like sending an email, the impact will generally be positive, but it just will vary in size across the population. For example, if you offer a reward to people, very few people will hate that, but the impact will differ. And so to encourage that, to encourage this kind of segmentation, to encourage the models to learn the segmentation, I have a different policy where I introduce an artificial treatment cost equal to the average treatment effect. So to get a good score, you need to distinguish impact below average and above average. And in general, if you have an actual policy, like you have a reward and rewards, and you give, say, $100 to your customers, hoping that they'll stay with you and spend more, you could use this also as your policy. Then for the hard part, which is automated model selection. We have EconML with its wealth of models. We have DoWhy, which among its many wonderful properties provides a unified interface to EconML. For example, it allows you to supply the same data frame to every model rather than having to slice the right bits as NumPy arrays and then pass in the names separately as in the EconML interface. So it's a wonderful interface. And then I also implemented a couple of extra models, most importantly, transformed outcome, which is mangling the treatment and the outcome variable to a single variable, which you can then, so you can regress that directly, and that gives you an unbiased impact estimate, and a dummy model, which is purely average treatment outcome plus randomness, which is something we'd have to beat, and we'll see how hard that is. And then I use FLAML, which is my other favorite Microsoft library. In general, I have to remark it's quite amazing for somebody who grew up 20 years ago thinking of Microsoft as the evil empire to see of all these cool stuff, all these cool libraries, which I picked not because they were from Microsoft, but because they were actually the best at what they did. In my opinion, they were the best. And so I used FLAML, which is a lovely AutoML library. And I even used it twice. First of all, I use FLAML models, FLAML AutoML class as the generic regression. So whenever the models need a regression component, I throw in FLAML into there. And also, if they need a classifier, I use FLAML classifier. The only exception is if my sample is actually random, I use the dummy classifier as a propensity tree function. But then also on a second level, I use FLAML for model hyperparameter and estimator search. And first we run each model with its default values, and then we start searching. And before I dive into the details of how we apply this to Wise data, I would like to note that this library is already available. It's open sourced at this URL, transferwise/auto-causality. And we've extensively used it for binary treatment and random assignment, so a dummy classifier as propensity, which is your standard A/B testing setup. And the repo also has an example notebook with a full cycle of ingesting data, producing lovely animations. Not animations, but lovely visualizations, most of which, again, just come from DoWhy and EconML. And the things that are coming very soon, they're just in testing now, is multivariate treatment and slightly non-random treatment assignment. For example, if you want to bias your random assignment towards things you think will have more impact, but will still want to keep learning, and some other things. Now, the next big step to plan for it is also to extend it to the instrumental variable models from EconML. And we could also use some help when reviewing the hyperparameter search spaces, which we kind of cobbled together from the EconML docs. And the forest model, we couldn't really get to work on large sample sizes. And the tree-based models tend to overfit. Maybe they could use some early stopping. And my favorite question, how do you cleanly score instrumental variable models out of sample? Because all the methods that I presented before only work for the regular conditional treatment estimate models. Now for the fun bit, which is how do we use it? Wise has the advantage of being a very decentralized, almost twofold, and product-centric business. So rather than go searching for use cases, the only thing I had to do was to give some talks at various occasions about how wonderful this new tooling is. And then people would come to me and say, we have this great business use case, can you help us? And right now we have two of them running. One is email campaign impacts, and the one I'm going to talk about is improved targeting of referral reward programs, where people can recommend Wise to somebody else, and then they get a reward if this other person signs up. But we also plan a wider analysis of A/B test results. and things like customer support impacts on customer retention and future behavior of customer support turnaround time. And in general, as Judea Pearl himself is very fond of pointing out, quite a lot of analytics questions are questions about causality. And if we can just do better at answering the very simple ones, we can add a lot of value. So, extra referral rewards impact analysis. We have in this particular sample almost 500,000 customers, and all of them can earn rewards by recommending other customers. But to some of them, a range of special reward programs, like limited time, extreme increased rewards were offered. And here I just grouped all of them into one kind of extra reward. So I had regular rewards and I had extra rewards, which were better. And the whole thing ran on on the machine with 100 gigs of RAM. And the only thing that's still left to set, because FLAML will take care of the rest, is the time budget for the component models, which was 10 minutes, and the total time budget for one run, so one target variable, is 3 hours. And there is a bunch of customer features like the base currency of the customer, how long they've been with us, the recent transaction value, etc. And the results are interesting. First of all, here you see the graphs of expected policy value. So the outcome, expected outcome, if we applied the policy suggested by the model for different models. And the model type is encoded by the color. And on the x-axis is the performance at on validation. And on the y-axis in the test set, which we didn't touch until we started generating those plots. And the black asterisk is the dummy model, which has no segmentation whatsoever, is purely random. So it's correct on average, but its differences from average are just random normal. And so for the three variables we try to predict, the results are quite different. For the post-boost referrals, so did actually this person refer anybody? The most models do worse than random, and one model does spectacularly well. For the post-boost converted referrals in the next 10 days, so which customers from which host actually converted, actually did a trade with us. We have a much saner correlation pattern, and some models are worse than random and some are better. And then when we try to predict not whether the customer converted, but how much volume they did, the data is all over the place. And that's probably because of the variance, because how much a person spends can obviously vary across a couple of orders of magnitude. And looks like with our data set size, we couldn't handle that extra variance. Now, the other interesting bit, and please don't be scared, is if you look at the average treatment estimate for the whole sample produced by the model against the same thing on the x-axis, which is expected policy performance. And what you see is that the very best model, which is the brown one, predicts a huge estimate. It predicts a huge estimate for the policy value. So we get more than 1% extra customers converted compared to the dummy model. But its treatment impact estimate is just 0.3, so it's not really consistent with itself. So it's probably not great to go with. And here again you see, but also you see how much noisier the dummy results are across the different data sets. So the small dot is the training data set, the medium dot is the validation, and the big dot is the testing. And you see how much more volatile the treatment estimate is across the two data sets for the dummy than for each individual model. Because the models actually take care of they make use of the features to abstract the variance. And then you can just split your out-of-sample outcomes by where the model says treat and where the model says don't treat. And look, and again, the model hasn't seen this data set on training. And you actually do see that the outcomes are very, very different. For the one the model says don't treat, the outcomes are zero-ish and even edging into negative. And for those where the model says treat, they are clearly positive. So you get segmentation. And then finally, to estimate a policy, you do need to estimate monetary value, not just whether they converted. But then you can do it in the second step, where you have a causal model for whether customer converted, and then a conditional model. If they converted, this is how much they're likely to spend given all the other variables, which is just your regular ML model with no causal inference needed. Probably use FLAML again. So it's still quite learned quite a lot, and the one amusing thing we learned is a new kind of data leakage, which is causality leakage. Namely, even if you don't look into the future and don't peek at a target variable, but if your treatment is correlated with features and you don't account for it in your propensity to treat model, some of the models, especially the Forest DI learner, can get fantastic scores. Like you can see here, the Forest DI learner predicts segmentation, which allows you to double your spending per customer if you target it right. Which are completely not real, and it's just leakage because your propensity to treat model is misspecified. So, coming back to the original topic, how can causal inference supercharge your A/B testing? And A/B testing is something that matters a lot to any customer-facing firm, which is pretty much most firms. You can use the same A/B testing data, just enrich it with extra features per customer. But now you can segment customers by impact. You can, and even more interestingly, because you can now specify a non-trivial propensity to treat function, you can also do biased random sampling. So you learn a bit of an impact, say, these customers are more likely to respond to this kind of email. And then you start biasing the emails for that segment towards that, but you just bias them, keeping the randomness. And this allows you to keep learning and do a kind of a Thompson sampling, not on the whole data set, but on customer segments, discovering them as you go. And most wonderfully, you could do all this with no prior expertise in causal inference, just a big, largish computing budget. And I really hope that you will try using it and let us know through the issues there and through contacting me what other things could be improved there. And I would really like to thank Per Morell, Mark Harley, Timo Flesch, Guy Durant, Wen Ko, and Xian Ziang for contributing to the package and for helping it bring it this far. Thanks a lot.
Thank you so much, Igor. That was a super fascinating presentation, and I'm really excited to have learned about the work you've done at Wise on using causality to improve your A/B testing. I'm looking forward to digging more into some of the details and taking a look at your code as well to understand it better.